Good morning, and today we have another regression model to show, and we're going to extend it in two ways. The first is to show you how to plot residuals as a way of diagnosing whether your model was well fitted, and the second is to look for outliers, or what are also known as influential values. So those are single points that by themselves have a strong influence on your model, which generally we don't want. Generally, these only come into play when your sample size is relatively small. And so we have an example today where we see that. Okay, and so we're going to look at a new data set that we haven't looked at before called boneden.dat.r data, which is from a study of bone density measurements among twins. And you can see there were 41 observations. So there were 41 twins were found where one twin was a smoker and one twin was a non-smoker. And the bone density was measured, as well as a bunch of other things. And the goal is to see if smoking influences some various kinds of bodily measurements. But we're going to just look at bone density in the lumbar spine to be specific. And if we look at the data, we see there's a bunch of variables, but we're interested just in LS1 and LS2, which stands for lumbar spine. That's our bone density measurement between twin 1 and twin 2. And also we are interested in PYR1 and PYR2, which stands for pack years, which is how much was smoked, either the number of packs times the number of years. And you'll see that P year 1 is always 0, that's the non-smoking twin, and PYR2 is some positive number. Okay, and so you can see that there are twins who smoked a lot, as high as 48 pack years, and relatively little, 5 pack years. Okay, so what we're going to look at in our regression model is the difference in pack years between the twins and difference in bone density between the twins. And so I create two new variables called pack diff and LS diff, which are just the difference between those two. And we run a model where the bone density difference, LS diff, is a function of pack diff. Okay, and we look at the summary, and we see that the relationship is negative, that bone density goes down with smoking, but the p-value is not significant, it's 0.14. So, no evidence of relationship here. If we plot those results, we can see that we do have a negative sloped line, but you can see from the confidence intervals that are colored in orange that it's possible that you could have a slope here that would be positive going across these data. So we're not confident that there's a relationship here. And we also see that there are quite a few points that are pretty far away from the line. And we have what looks like a general downward trend. It even looks like the downward trend should be steeper than this. But we do have this one stray point up in the top right that's unusual, where the greatest difference in pack years between the twins, which is more than 60. So one twin smoked an enormous amount, and that's a pack a day for 60 years. And that person actually had a higher bone density than their non-smoking twin. So we might think that if it weren't for this point in the top right, maybe this relationship would be stronger. So we will explore that momentarily. But first, we're going to look at the residuals from this model. And so there happens to be a variable in the model output which I called model in line 10, there happens to be a variable called residuals. We've seen this before, and there's also another variable called fitted values, fitted dot values, and those are the same as the predictions. And so it's possible to use the cbind function, which is column bind, to attach the columns together. So we'll get, in the same data frame, we'll get the fitted values or predictions, we'll get the residuals, and we'll get the original data. So I'm going to run line 19, and I'm going to call that bone den 2. And if we look at bone den 2, we see at the beginning, because the cbind function goes in order, and I told it to put fitted values first, residuals second, the original data third, we have fitted dot values first, residuals second, and then all the original data. And if we look at the first point on the left of this graph, we can see the red line, which is the prediction, is about negative 0.02, and that is the fitted value for 0.1. And if we look at the prediction, if we look at the actual point for the first observation, that is ls diff, and that's negative 0.05. And the difference between the red line and the black dot is our residual, and that is about negative 0.03. So you can see how these data values correspond to the graph. I don't like the names of these first two columns, so I'm going to change them using the call names function to predictions and residuals. And so now, if we look at bone den 2, we will see easier names to work with. Okay. So now I'm going to plot those residuals. And so I'm going to use the exact same format as lines 14 through 16, except instead of the y-axis being the difference in bone density, I'm going to make the y-axis be the residuals, or the errors in between the predictions and the actual values. And I changed the colors to blue and green just to make sure it is not confused with the earlier graph. And we see that the residual best fit line is perfectly flat and right on 0. So this is good. This is what you want. This means that the model was well fitted. It has no slope, meaning there's no structure, there's no relationship between the residuals and the data. Okay, so this is a good diagnostic. You can get this from the graph as well. It's a little harder, right? So here you're looking to see if the points above the line and the points below the line are roughly equally balanced and not getting the distance between the lines is not changing a lot. So plotting the residuals directly, as we do here, is a more guaranteed way of making sure that your model was well fitted. Now notice we have this point in the top right where the pack difference was greater than 60. So our same point that we had back here that we thought was a little suspicious also happens to be our largest residual. It actually is, there's one other point down here which has a similarly large residual. So the difference between the prediction and the model here was not very good. So that's another piece of evidence, maybe to look at this point skeptically. And so I'm going to remove that point, and I'm going to make a new data frame called boneden_remove1. And my criteria is just remove all the points where the pack difference is less than 60. Okay, so now the way I'm doing it here is a little bit contrived, but it's possible that you could justify this by saying that given the ages of your subjects, it's not plausible that there could be such a difference, and perhaps and so you maybe have reason to believe that this is some sort of data error, typographical error, perhaps. in any case, we're going to remove it. And so now we're down to 40 observations instead of 41. And I'm just going to repeat the same exercise that we did before. I'm going to build a model, look at the summary. Now, instead of a p-value of 0.14, we have a p-value of 0.008. So now our relationship is significant. So it does turn out that this one stray point, this unusual outlier point, was by itself preventing our model from being significant. So this is what you would call a influential value. And in general, we don't want these. Sometimes they can't be avoided, but in general, we don't want these. And so the book actually covers in some detail a few other methods to identify and remove these. What I'm showing you here is perhaps the simplest way. I'm going to plot our data again, and so again we have a negative relationship, but this time the confidence intervals are narrower. It's no longer possible to draw a line across these data that has a positive slope and remain within the confidence intervals shown in orange. And so again, that is proof that we have a significant relationship. We still have some points that are pretty far from the line. Notice the graph now cuts off at 50 instead of 60 because our maximum value is now about 48, whereas before it was 60 something. Okay. Final thing I'm going to do is do another residual plot, and I'm going to do the residual plot on the new data where I've removed a point. So lines 37 through 39 are the same as lines 19 through, same as lines, where was it? Same as lines 19 through 21, except I'm working with the data where one point has been removed. And I'm going to make a plot of the residuals of our new model. And again, our slope is 0. That's good. That means we have a well-fitted model. We no longer have a residual that is 0.2. We still have our negative 0.2 residual because we didn't remove that one. Okay, so that covers that. Thank you for listening.